Welcome and thank you for this chance to give this talk. So, first of all, I would like to introduce the title. So, towards a smart urban water supply system. Now, the smart there, many people are using it now. Usually people, when they hear the word smart, they usually think of something like this. So they look at the Tesla car that is automatic. They look at these fancy things. This is, high tech, or this smart trash can, or all of these sensors and big data and IoT that people are working on. But the thing, what I'm trying to show today here is not exactly this. So it is still smart. It has a vision to go towards technology that can apply things like this, but mostly we're trying to develop the fundamentals that can be studied and build the background so that technologies such as these can be used, and then you will have a truly smart sensing data system for water system. Now let me introduce the project. It's a theme-based project. It's a big project that we started 3 years ago. It's called the Smart Urban Water Supply System. I'll just give a brief introduction first, and then later I will show some of the results and the method that we are using. Now, the idea started with basically water. Water is very important and people need it, and mostly these defects in the pipe systems that are occurring everywhere in the world. So you have leaks, you have bursts, you have blockages, you have malfunctioning devices, and all water supply system departments all over the world, they are complaining about these things. Now in Hong Kong, we actually have about % leakages, but overall in the world there is estimated about 40% of this water is actually leaking out. That's a big loss of water, plus it's a big loss of energy, because we actually spend a lot of energy to pump this water, and later on we just found that 40% is lost. Now, water supply systems, they're very complex. You all know that these pipes are underground. You have no access. So things are just happening, and you don't know what's happening. You don't know where the leak is. You don't know where the blockages is. And even if you know, it takes a lot of money to go and fix it, because you have to interrupt the roads. You have to stop everything. You have to dig a hole and do all of that. Now, the current solution for leak detection and blockage detections, these are the most advanced system, the Sahara system and SmartBall. This is the most advanced state-of-the-art for leak detection that exists now in the world. This system is basically to send a sensor that moves with the flow, and a guy here listen to this sensor, and if there is a leak, you will detect it. This one, it's a ball. This ball, you basically put it in the pipe, and then you have to fish for it. Now, what's the problem with these things? They're all passive. They're still very limited, and currently we still have a lot of leakages, even though people are using these systems. The problem with this technology, they call it the smart ball, but yet it costs about $5,000 to $7,000 US. And after they bought it in China, they bought it, and they end up 70% of them, they become blockages, because you put them, they try to fish them somewhere else, but you don't find them. They get stuck somewhere, and then they become themselves a problem. So you need to think of something else for these leak detections. Now, what we're trying to think is actually mimic other fields, which uses waves. Now, waves, we are very used to the idea that you go to a doctor, you do an X-ray, you send electromagnetic waves, and that will give you images of what's happening inside your body, inside your system, right? Sonography is the same thing. You can see the baby, what's happening if you send acoustic waves, ultrasound, and then show you the form and image of the baby, right? Some of these waves are used also for defects inside material, and people are using it also for oceanography. Now, we're trying to do the same thing, but with pipelines. Instead of calling it X-ray, we call it transient-based defect detection method. Transient is mainly acoustic wave. That's what we mean by transient wave. Now, the way it works, you have a pipe system like this, and then you come somewhere at a given boundary. This boundary could be a fire hydrant. You go to a fire hydrant, you open the water. This is what we do in Hong Kong. You open the water and you close this valve suddenly, for example. Then you create a wave. This wave will start to propagate inside the pipe, and this is an image what's happening for the signal as you measure here. So as you measure, you meet a leak, a reflection will happen. You meet a blockage, a reflection will happen. We get the signal, we study the signal, and we do some signal processing, and we can tell where the leak is, where the blockage is. What's great about these methods is they are very quick. The wave speed is about 1 kilometer per second. Now, to feel that speed is about 5 times the speed of an airplane. So when we go to the field, within 5 seconds, we do this, we finish the test, we take the data, and we show you what's happening. That's ideal, of course. There are complications which we're going to show you. Now, this is the basic idea. Now, the vision of a smart system. What's the vision? The vision is having a network like this. You go to some access point. The access point can only be a fire hydrant because everything is under the ground. You go somewhere there and you send a wave. Initially, we send what we call low frequency wave. Low frequency waves, if it's at low frequency, the wave can propagate for a long range, kilometers. Okay, they can go up to 5 kilometers. However, the resolution is very bad. Means it cannot tell you exactly where the defect is. It can only give you an area. This area could be 100 meters, 200 meters, right? So what we need to do, once we know that the defect is somewhere in this area, which is a region, then we need to go somewhere closer and send a high frequency. High frequency give you high resolution. This is also in medicine is the same thing. You go to these ultrasound, that's why they use ultrasound, is high frequency. X-ray is also high frequency. So once you do that, then you have high resolution. The range is very short and you get high resolution. Now, this is basically the vision. Send waves, low frequency, get a possible area where the problem is, send high frequency, get good resolution and tells you where the leak is. This is what we do for the project. Now, our project is basically has 4 tasks. Now, one task is design experimental setups to validate any results that we do or we need to validate. Task 2 is basically a forward problem analysis. This is the mainly 2 tasks that I usually lead in this project. A forward problem is to understand how waves interact with defects. So if there is a leak and send a wave, what will happen between the wave and the leak? How do they interact? What kind of reflection I'm going to get and why? This task is talking to signal processing and inverse problem. Inverse problem is basically mathematical algorithm that tells you, you get some information, you run the algorithm, it tells you where the leak is or the blockage is. So these are the detection methods that are here. Signal processing is, you all know what signal processing is, what type of signal I have to use, how do I reduce the noise, and all of that. Now what I'm doing, I'll show you some work that we did here, and then I will go through the different facilities that we have and show you some examples of the data that we get and the type of detection that we are doing. So I need to introduce this. First of all, we go to a pipe system, we send a wave, and we measure this wave using the transducer, and we get the signal in time domain. This is the type of signal that we get and what we call usually a water hammer type of signal. Now, we work usually at frequency domain, much easier to do signal processing in frequency domain. And then we study the modes. These are resonant frequencies and resonant modes, and what sometimes you can call them descending waves inside the pipe system. Now, the type of questions that we ask in task 2, something like this. If you have a blockage and you measure a response of a pipe system. The blue one is for an intact, the red is for a blocked pipe. You can see there is a difference. The difference for sure show you that there is something happening, right? Now, we found out that this shift between resonant frequency can give you information about the length and the location of the blockage. Now, there has been methods that applies, just take that information, put it in an algorithm, tells you where the blockage is and tell you how big it is. But task 2, what we mean by a forward problem is basically this. When I see a shift going to the left and a shift going to the right, the question to ask is why? Why did that happen? Why a shift has occurred? Why did it go to the left? Why did it go to the right? So that we understand how the wave is interacting with the blockage. Now we study that, we simplify the problem, and we look at the wave propagating and there is a blockage, and we look at reflection, how much is reflected, how much is transmitted. We do that, we end up with something quite nice, that there are some frequencies at which the wave transmits the most, and some frequencies at which the wave reflects the most. So this is what we call maximum reflection frequency, and this is maximum transmission frequency. It turns out that this is a very fundamental thing that happens in physics. This phenomena is called Bragg resonance. Bragg resonance is something big and known in physics, and these two people, Bragg, the father and the son, they got a Nobel Prize for this Bragg resonance. They studied this and they found that there is maximum reflection and maximum transmission occur in crystals. You take a crystal, you send a wave, you see how much is reflected, how much is transmitted, and they end up by telling you what is the shape of this crystal. And at that time, it was a big thing to characterize crystals. So, physically what is happening, you send a wave, the wave at the blockage, some of it transmits, some of it reflects, right? Now, this transmitted wave also will reflect back. Now there is a question. If the frequency is such a way, this reflection comes out in phase or in opposite phase. If this comes out in phase, then you have resonance, because the wave superimpose. But if it comes out in opposite phase, then nothing is coming back. They kill each other. That's how you end up by having maximum reflection or a total transmission. So here I show you a video that is to help you see these things. This is the case for a total or maximum transmission. This is a pipe. You can look at it as a pipe. This is the blockage, and I'm sending a wave from here, and these are open boundaries. Okay, so wave will come from here, and we'll see how much reflects, how much transmits. Normally, we should have a loss of transmission if I choose the right frequency. So I speed it up manually, and here is the wave coming. So the wave comes, arrive to the blockage, and then it go through it, and you can see that the wave easily going through it. A bit of resonance happens here, but the wave is almost all of it is transmitted. You almost see no reflection. That's for what we call Bragg resonance of maximum transmission. Okay, very little reflection comes back because you cannot have a single frequency sine wave. Now, look at the case of maximum reflections. Same design, same blockage length, same things, but the frequency is slightly different for maximum reflection. You send this wave, comes in, and then suddenly you can see that this is how much is reflected and that's how much transmitted. You see now the reflection is very big, the transmission is little, right? A video that is always exciting for me to see for Bragg resonance, this is the case where we build many blockages that actually reflects, And you can see that you can stop the sound from passing by for a given frequency. They try to go, but because of Bragg resonance, you have many of these blockages, 6 of them. You can see now nothing can go through, right? You keep sending, you resonate here, but nothing is going through. So this is a physical, this is what we call a forward problem. Understand what happens. Now, because we understand what happens, we go back to our problem, to the blockage, and now we know exactly why it shifts to the left and why it shifts to the right, and is well connected to Bragg resonance. That helps us actually to improve all the previous methods for blockage detections. The same thing also happened for leaks. I'll just go through it quickly. If you have a leak, then you have a leak at this boundary, and you have a boundary like this, and you see that the Bragg resonance also occurred between these two layers. Okay? The question that we ask here, maybe not clear, but there is a red color and blue color. The blue is for impact, the red is for leak case. For the case of a leak, there is no shifting. These resonant frequencies don't shift, but their amplitude becomes different. You see, this is here, this is a bit lower, this is high, low, and you have kind of an up and down in the amplitude. That up and down turns out to be also related to Bragg resonance. And that's what we call forward problem analysis, to understand the physics. So basically the same thing. I want to go through this quickly. And Bragg resonance gives us a big information that if you see a big drop in amplitude, that's because the lead for this mode is located at the maximum pressure. Now you can think about it. If a leak is located at the high pressure point and you have a leak, then you can push the water out. If you have energy, you push the water out, you relieve the pressure. It drops. And that's why we see a drop for this mode. The pressure is high, pushes the water a lot. The water comes out, the pressure, the amplitude drops, and this is why we notice there is a drop. However, if the leak is here, which is a 0 or a node pressure, then you see no drop of amplitude. That's why you see up and down. You have different modes. Some of them have high pressure, like this one and this one, so they drop. However, this red one doesn't drop. The second mode, you see the amplitude is quite high. That's why you see an up and down. So it helps explaining what's happening, and it helps improving the leak detection methods, and it did. Now I go back to the slide just to tell you that now I'm going to go through different results that we found, different methods that we applied, and the way I do it, I will show. If I show experimental setup, then that's task 1, and then what we do for task 2, and then what we do for task 3. Now here is our first experimental facilities. So we have 3 in Hong Kong. One is a totally field experiment. The water supply department, we work with them. They give us a place with about 700 meters, a true network. We have access to 4 or 5 fire hydrants. We mainly work with the 3. So it's somewhere in the street. It's quite nice, quiet. We can go there and we take this fire hydrant and we modify it. So we have access from here. We put the valve, we put the flow meters, and we get water out. We close it and we measure. We measure at the different fire hydrant. This one is this one. So we sit here and we do our measurement, the computer and everything. So we did this. What we do, we simulate a leak. We put the leak here, and we come to this fire hydrant and we suddenly open and close the valve. And we get a signal. This is the signal, one with impact, no simulated leak, and one with a leak signal. Somewhere the leak has occurred. We do now inverse analysis. So now we have the data, we understand what happened, we apply an algorithm to do. So in this case we did ITA, inverse transient analysis, and this is our detection. The true leak location is here, this is location, and this is our detection, here and here. Now you look at this, you say, well, you did not really detect the leak, but given the complexity, how sharp is your wave, because this is low frequency. You go at low frequency, that's why you don't get good resolution. the best resolution that you can get is within your wavelength. In this case, our wavelength is within 30 meter to 40 meter. So that's why the resolution also will be within 20, 30 meter. You cannot get better than that unless you send high frequency. We haven't sent high frequency here yet. But that's actually for water supply department good enough. If you show them within 30, 40 meter where the leak is, they can go there and investigate and listen and they get it right. So this is some of the results that a student is working on, Wakar. Now this is the second facility. This is in a Beacon Hill reservoir. It's a reservoir, belongs to the water supply department. What they did, they give us access from a main pipe. They say, okay, you can take access from it and then build your own pipe. The pipe is 6-inch, it's quite big, quite large. And we build about 150 meter pipe around it. So this is kind of a reservoir. We have an intake from a main pipe, a true main pipe, and then we build our own pipeline. And this is how it looks. Same thing, we measure different locations and we have different places like this where we have leaks. We can simulate leaks and we study what happened. And we have a pressure reducing valve, kind of a dynamic boundary to add in some complexity to the system. These are some experimental results. We see different leak sizes, because sometimes you can detect a leak, but how big is the leak? If the leak is very big, then water supply department will tell you what anyone can see that leak, right? So we do small leak, very small, small, medium, and large, and then you can see a difference between them. The leak is somewhere here. You can see this drop is getting bigger and getting bigger. Transient, inverse transient analysis. You can see that as the leak gets smaller, the detection is not that big. So, but of course, you still can catch it, and we keep on improving these methods because you still have some noise that you have to get rid of. So, if you study multiple leaks, in this case, for example, 2 leaks or 3 leaks, we are still be able to detect it. Of course, you cannot give exact location, but you can get close enough. These are real data, right? And this is the case where we found out that leak detection is very sensitive to the pressure. If you go to a Hong Kong is all mountains. You actually have to rise buildings. So the pressure usually goes up to 10 bar. Very high pressure in these pipes. We found that the higher the pressure, the more difficult to find leaks, because leak reflections depends on the impedance, acoustic impedance of the leak. And this acoustic impedance is proportional to the pressure. The pressure is high, the impedance becomes very small, and then you get small reflections. So we studied this. We found that if the pressure is 2 bar or 3 bar, the detection is good. But as the pressure becomes higher and higher, the detection becomes very little. So that's a big problem, and we're trying to find a way that even at high pressure, how can we manage to still detect leaks? Now this is another forward problem we've been working on. This is probably so far is my favorite one. This is fascinating. Usually you get damping from a signal, right? You have viscoelastic effect if you have a plastic pipe. You have friction in pipeline. You send a wave, the wave will start to damp. Now what this student is doing is try to reverse, and wherever it has been damped, he can actually reconstruct it back. Now look at this black line. This is numerically a signal with the friction and viscoelasticity terms. Now you can see you have damping, right? The pressure is getting reduced. What this guy do, he will take this signal, the black one, put it in an algorithm, and then bring back the intact case. So as if no damping has happened. And that helps us a lot, because usually you lose signal, you lose information through damping. Now there is an algorithm that can build back or give you back the undamped signal. And that way our detection becomes much better. Now that was able to do it because he can find a linearized relation between the damped signal and the undamped signal. So that's the relationship that he can build, therefore, this gamma 0, which is the impact case, from this one. This is what we measured, this is experiment, and this is from the model. If you give me this, I can get this one. So we go to the lab and we try to validate this. This is HKUST lab, university. So a lab, it has 150 meter. You can look at this complex system, you say, why these people are crazy? You're making complication, lots of bands. Now the reason is, Hong Kong is very small. Hong Kong is tiny team. The space is a big problem. So even for 150 meter, we have to go around the lab. Our lab is very small, maybe as big as this one. So we have to go around. So we go around the 3 times, and we have a pipe. We pump the system from this pump, and this is our downstream end. We get the signal. The blue is the damped one. This is the damped signal. The red is what we bring back for input. There is some noise, for sure, but you can see that this high frequency, the sharpness of the signal is coming back. And the more the sharp is the signal, the better is the detection of defects. For example, this is defect detection. This is what we call area reconstruction. You go and measure the signal, you give it to me, I put it in an algorithm for area reconstruction. Area reconstruction reconstructs the area like an image for you, how the area of a pipe looks like. So if we don't bring back, I mean, this is a comparison with using damped signal and undamped signal. You can see that one before correction, one is after correction. Look at this case, for example. The blue, the red one is without correction. You can see that the blockage, we have a blockage here, and the blockage is poorly detected for the red one, right? But for the blue one, you get more sharp variation. So bringing back the damping, the information loss, actually give you better resolution. So these are some sort of examples what we do. Now, accuracy is also important if you send the right signal. Sending the right signal is very important. If you send a valve closure signal, like a step function, it turns out it's not that good. So we found that sending a PRBS signal, which is a random sequence of open and closing a valve, is very important. And recently we started to build valves that we can control in such a way we can send any signal we want from the valve. This is just a quick video to show you a valve that we just constructed that open and closes, and you can control the speed, the position, and everything. So this is 3/4 inch pipe, and this one is a 4 millimeter pipe. So this is the valve, this is the linear motor that we just showed that it can be quite fast to open and close these valves. So just an overview of what we have and what we're trying to do. So how much time do I have left? Because I'm losing record of time, but I'm trying to go fast. So I just now want to introduce what we do for high frequency, very quickly. So what we showed before is low frequency. Now high frequency give you a high resolution, what we can do with it. Now what's high frequency? For low frequency you can use one-dimensional model. You have a plane wave, you have 1D, you can use method of characteristic, and this is the signal that you get. Now if you go to 2D model and you do truly valve closure, you end up physically seeing something going up and down. This is not noise, this is actually quite physics. If you take it, you put in frequency domain, you end up with the frequency corresponding to the high modes of high frequency. So what happened is when you suddenly close a valve, you actually can excite high modes. These high modes, the difference is a plane wave. For 1D model, you assume that the pressure is constant along the cross section of a pipe. That's what we call a plane wave 1D model. However, for high modes, the pressure along the cross-section of the pipe area is not constant. It varies. That's why this is a pipe, and this is the cross-section, and you can see that blue and red and blue. So the pressure is different along the cross-section at high frequency. So that's very important. We have to take it into account. I'll go quick about this. This is just 2D model for high frequency to show you that there is a cutoff frequency from which high mode starts to be excited. If you come here, this is a group velocity, this is a plane wave, and these are the velocity of different modes. If you send frequencies, wave at these frequencies, far away from this cutoff, then you have a plane wave. A plane wave simply propagates in a straight line. Okay? That's it. That's a plane wave. You can look at it if I have a video. And this is a plane wave. You can see the pressure is constant. You send it, the pressure is constant. Same color, same color. That's a plane wave. Low frequency, plane wave. Now what happened at high frequency? You go to higher frequency more than F1. F1 is a cutoff frequency. So you're exciting this high mode. Now, the wave propagates in an oblique pattern, right? You go up and down, down and up. That's what we call a multipipe effect. So to have a visual for it, you can click on this. And you see now, you send, you get a plane wave. This is a plane wave, but you also get a high mode, one high mode. You see the pressure, positive, zero, negative, and so on. So the pressure varies radially. This is what we call plane wave mode, and this is the first radial mode. So high frequency, you get this complication of dispersion. Dispersion means different waves propagate at different speeds, and you get these high modes. There are complications, but they also, when you study them, you can make use of to do some detection. Now, what we try to do, we have a setup of a lab. We have a short pipe. We don't need a long one because we said high frequency, high resolution, but it only needs to go for a small range. This is a 6-meter pipe long, 3-inch in diameter, and we have also 6-inch, 2-inch different diameters. Now the objective is to send a wave. This is our hydrophones that send high frequency waves based on piezoelectric material. And let's say you have a blockage, you send a wave, you get reflections. The reflection will also come back with high dispersion. But when we do inverse problem, we found that we can actually get high accuracy, exactly the location of the blockage. So the resolution is unbelievable. I like to show some equipment because these high frequency waves are very fancy, and doing the test and the math is not difficult, but choosing the right equipment, doing the setup took us nearly 2 years to get this done. You need a very good amplifier, no noise. B&K is a very good company. Data acquisition system from NI. You have a B&K signal conditioner. You have this B&K hydrophones that goes from 5 kilohertz to 70 kilohertz. And these are accelerometers, 3-axial and uniaxial. This magnet that you see here is used to control this hydrophone. If you would like to change the position, location of this hydrophone, underneath this magnet there is this one. And if I push the magnet backward, the hydrophone will move. Right? So that's how we can move and choose different location for the source. Now, these are what we call the dispersion curves for high modes, because these are high frequency. So this is from analytical model, and this is from experiment. The matching is good. I'm not going to say perfect, but it's good for what we need. Once we have a model that we validated that is not bad, we actually now have a model, I have experiment, you match, and then you can do inverse transient analysis. This is the comparison. This is the type of source that we send. This is experiment, and this is analytical. It has a bit more dispersion than analytical, but that's not a big issue. The first thing that we did is time reversal. Time reversal You send a wave, you receive it, you get some dispersion. The question, can I reverse it back? Right? I would like to know what happened. What is the source of this signal that I have received? I can record this one, flip it, it's flipped, and then send it back. I send it back, I found almost the same shape. So that's great. This is what we call time reversal. Because think of this source being a reflection from a blockage or being a reflection from a leak. If I can catch it, I take it, send it back in my model, reconstruct the origin of that reflection. Where is it coming from? At which location? That's what we do. It's called match field processing or time reversal. This is a signal that we detect from a source. You send it from here, you record it, you flip it, you send it back. It tells you the location at which the energy peaks. And this is exactly the location of the source. Right? So that's what we do. We send the signal and we apply match field processing. This is a numerical case for, we have a CFD code, 2D, and high resolution and high order of accuracy. We get nice data. These are the high modes. This is what we catch. We take this one and we do time reversal or MFP, match field processing. We get exact location of the blockage. Right? So 30, it gives us truly 30. But this is no noise, of course. So basically, that's the end. And there are many other things. If you have any questions or you would like to discuss, I have different things even later on or tomorrow. I'm happy to share with you anything you want to know more about the blockage. So thank you very much.
We have 5 minutes for the next lecture. So if there are any questions.
I would like to ask one. Thank you very much for the presentation. I've been following the work of Mohamed Kidoui. Is he your supervisor or colleague? Or?
Yeah, he's my former supervisor. Now I work with him. We're colleagues.
Your colleagues at the
he's the project coordinator for the he's the PI for this project.
Okay.
And I'm a coordinator for 2 tasks. So.
I've been following his work for a while now, and I think it's fair to say that out of all these groups that are doing work on transients for leakage detection, this group, your group, is probably the most advanced. I mean, Brian Cumming was doing a lot of good work, still is in Canada, in Adelaide they do good work, in Italy, Bruno Brunone and Marco Ferrante. But I quite like the direction in which Mohamed is going. Now, having said this, I've done some of this work myself about 20 years ago. I have to tell you that the general feeling in the water distribution systems community are mixed about these transient methods, okay? Because a lot of this work still seems to be confined to laboratory setups. Or even if you're dealing with field tests, again, there are no real networks involved. It's always kind of a long pipe with some sort of excitation on one end, and boundary condition on the other end.
Totally agree.
Yeah, and this has been going on for a fair number of years. I'm just wondering, can you comment on this? When do you see these methods kind of making the next step? Becoming good enough to be commercial, becoming good enough to detect leaks in distribution networks and so on. Because meanwhile, alternative technologies have developed, and there are now commercial solutions which are used by water companies which don't involve transients, but which are able to detect leaks. So in a way, this technology is competing with those other technologies. I'm just wondering, because basic research has been going on for so long, and I'm really fond of it. It's close to my heart, and I think you are doing great work in the group, probably the best in the world. I'm just wondering, when are you going to make the leap, the next step?
Now, that's a very good question. Here's what I think. It's very challenging to go to a field. Now, we went to the field. It's actually, you can consider it as a network. It's quite open, but it's confined. It's a long pipe and connected to nearly 12 or 15 buildings, right? With different.
There is consumption along the pipe.
Consumption and everything. So it's actually kind of a network. We were able to detect a leak, but it's a simulated leak, and it's a big one, right? And the pressure is quite high. So I agree with you. If I take this technology, go to any field here now, and try to apply it, 20% maybe you get something, 10%, right? So Bruno went to the field. He went to Trento. He went different places. He applied this method, and He has papers and show you that, yeah, I can detect it. He was able to detect actually.
In controlled condition.
Control, but he had 5 kilometers of a network, right? I forgot about where. But here's the problem. You go to the water supply department. There is no question that this can be applied, but I need information. So I apply this method because why do they work in the lab? I know my setup. I know my boundary. It's not because it's not complicated. We do a network, we can still get it, but I know my system. I go to the water supply department and say, all right, I have to make measurement here because my method needs some measurements here and I need to access the pump. So cannot. And this is underground. I'm not going to dig a hole and make sophisticated things and do it. The water is going off. So I asked.
At least they let you to the network. In the UK, they won't let
you. Yeah, I mean, they were nice
network.
enough. They were actually
because they already would cause immediate discoloration event or something with the transient.
Exactly. I mean, now here's the problem. You say you go to the water supply department and you tell them, okay, tell me what is happening here and there. Let me just show you the network. This is just a sketch, but it's okay. We only have access here, access here, access here. Now, we go to the water network and the water supply says, can I have access here? I need to measure here. No. 1. 2. You see these branches? They're all branches and network. This is actually a network going to buildings, going to different places. So that's actually quite complicated. Here's the question. You come to any branch here, any one of them, ask water supply department, what do you have there? I don't know. How is it connected to the building? I don't know. They have a pump. What is happening? I don't know. So it's totally up to the building. So we had to get the student and we go around this building talking to these people. It was a big issue. They don't give you some information, you collect some. So we have no idea about the boundaries. So boundaries are very important. If you tell me, if I am confident that if you tell me exactly what do you have here, here, there is 60-70% you actually can achieve.
But in reality, you can't expect to know all these things because in reality, in many other locations, you won't know exactly what's behind.
Sure, but now the world is going towards smart cities. Now, smart cities, you need a smart infrastructure. If you're going to build a new infrastructure, new cities, you need to design it first to be smart pipes. The pipes that you know their location, you have sensors in the pipe, you know what's happening there. You know, you have to find a way that converge with this technology. You cannot go to an old system or 100 years old or 50 years old pipe and say, what do I have there? They have no paper. This I have no idea. I don't know even when I built this pipe. But if we can meet, we do the research, we do fundamental work. It's still good and beneficial to do fundamental research. The day will come when smart cities will converge with this and we have a smart system, smart infrastructure. At that time, you have data, you have control. You can do it. So people are working towards smart infrastructure for that. So that's the hope, that hopefully they meet someone. But you will need 50, 70 years to get this code. I don't believe you can get it in 20
What are you
years.
going to do in between?
In between, you keep on construction because how long it took us to take an airplane or construct it, how long it take us to go to the moon, how long it take us to do this. So they all started for years and years. So how long it takes us to get X-ray, going? Now it's very simple. You go to the doctor, you say, can you really imagine you go to the doctor and tells you have a bone broken here and you have this? I mean, that's unbelievable. But within 50 years, people has developed. If you go 50 years ago to my grandmother and say, okay, we can do this for you, there's no way. No one can believe it. Airplanes, everything. So it takes time. But that's what research engineering is to have a vision. We're not doing in university, you're not doing engineering. You're not solving today's problem. You try to solve tomorrow's problem, right?
Yes, but your research is so fundamental in nature that it often has side results, side achievements. And
it's like finding out Bragg resonance was very fundamental. No one really realized that can be applied in pipelines. So a new math, a new reconstructing damping. I mean, damp is gone, and now you found it back. That's actually great. So you start to apply. So fundamental research is always beneficial to even teaching, improving everything.
Okay, that was a nice discussion. More questions?
Maybe a quick question, sir. Thank you for the very good presentation. I was wondering, in networks you will have bands and other places where you will have flow detachment and recirculations, which may create also some sorts of waves, probably at lower frequencies. Can you foresee a problem with that in a real network, or is such a deeper frequency that you could filter it out easily?
Very good question. Now, two things. One, in a pipe network, you have bands, you have flow circulation, you have turbulence. One thing, wave speed, waves, acoustic waves, and turbulence, they have a completely different time scale. One is at the flow velocity time scale, the other is at the wave speed time scale. Means by the time I send the wave and get my signal, the flow has did this. Nothing happened. So as soon as the turbulence starts like this, so nothing happened. So within a fraction of a second, you send the wave, you get it back, and the flow barely moved. So the time scale is very different, and therefore you can do separation of variable, and you can get it out of your system. If you want to think of it acoustically, that's what we call low Mach number. The velocity of the fluid is much lower than the velocity of the wave. Now, in terms of frequency, it's a good question. Why? Because a lot of research we've been doing to know the noise of the turbulence. So we go to the system, no transient, we just listen. We put transducer and we listen to the noise. We characterize the noise, and it turns out that it's quite close to a Gaussian type of noise. As soon as we know the noise coming from turbulence, then we can implement it in our model and take it into account. So we do both, but it's not really very important unless you go to high frequency. At high frequency, this turbulence and these eddies and this flow separation can really affect the signal. But if you find a way to model, that's a good thing. So that's why actually I was here and talking to David yesterday about band's effect. It's something we're trying to work on. Good question.
And what about other phenomena like pipe wall viscoelasticity? I've seen in the lab that you are using polyethylene.
Yeah.
Why polyethylene and not a metallic pipe? Because you will have the viscoelastic behavior of the polyethylene. Maybe it's not something that you want, no?
Well, we use both, but this is the main reason why in our lab we're using viscoelasticity is because the wave speed is much slower. If the wave speed is slow, I only need 150 meters. If the wave speed is 1,200, then I need 300 meters long pipe. I can just do that. And it's very easier to work with. High frequency also is because of the magnet. We do copper pipe and we do HDP because we have a magnet, and the magnet you can move, so it's not magnetic, right? Metal pipe will get stuck. How would you move the transducer inside? So nowadays, now starting in 2 months, we're going to start to build a small robot that can move inside the pipe so that we can move transducer at different locations, because you have to measure at different locations. So it's kind of a dilemma, but not preference. One thing for metallic pipe, we did air experiments in the air to actually mimic rigid pipe.
So then the strategy is slower.
Yeah,
So
it's slower in the air. It's still slow, but it's a rigid for air.
Great. More questions?
What limit of diameter are you working with?
Sorry?
Limit of diameter for this?
Diameters.
Yeah.
In our lab setup is a 3-inch diameter. It's about 10 centimeters. Okay. For the high frequency, we have different diameters: 6-inch, 2-inch, and 3-inch. These are the diameters we are working with. Low frequency and high frequency. So in the field, of course, you have 150 millimeter to 150 within 6-inch scale.
Have you taken all pipes from the real system with blockages to test it in your laboratory, or you simulate also blockages artificially? How do you work with that?
We did not take blockages from the field, no, but we mimic blockages basically by, if a discrete blockage, we install a valve, gate valve, and we close it. Or we change diameter. For example, you have a 3-inch, then you take 10 meters of 2 inches, and then you mimic by, a change in diameter. That's what a blockage will be for us. We are trying to mimic real blockage, doing a random shape
easy, right, to get it from the water supply company. One of these old pipes they change and before they throw it to the trash, just
to take it, to use it and test it, well, it depends on the material, but so far we haven't really get it or used any of it. Something. And it depends whether they give you.
In lab conditions, it's not that ideal to have a real blockage, no? Because friction is much higher, you have irregularities inside of the pipe that maybe you don't want when you are focusing on the fundamental, on understanding the fundamentals of the phenomenon.
No, but in Beacon here we can do it because it's a 6-inch, quite large. If we have the same diameter and they fit, yes, but quite challenging to use the same.
I think it is for a paper for Journal of Hydraulic Research.
Sorry?
I think it would be good for a paper in Journal of Hydraulic Research.
Oh yeah, but
It was a joke.
yeah, that's fine.
Okay, more questions? What else? Yeah.
Yeah.
Is there a different temperature of the water?
Sorry?
Temperature of the water?
Temperature. Temperature of what?
Of the water when the change.
No, a temperature of water is actually not important for this case. You know, water has a very high specific heat capacity, about 4,100. That means the change of temperature is very little. Usually our state equation will be isothermal type of thing. So we don't really care about change of temperature for water. If it's gas or oil, then you need to be careful.
Okay, so yeah, we need to leave it here because there is a Zoran lecture now. If you want to further discuss with Moed, you will be in the second floor during today, tomorrow, and Friday. So
sure, thank you. Thank you.